All right. Today, I'm going to talk about lattice energy. Okay, so the topic is one of the um, topic of A level. Okay, lattice energy. So basically, lattice energy is the amount of energy released when one mole of ionic compound, right, is formed from its gaseous ion, right? So under standard condition. So for example, we have a let's say I have a Na plus G, and then I react with F minus G, then the energy is released. So when the energy is released, it's actually exothermic. So you'll have a NAF in the form of solid. All right. So again, this is actually exothermic reaction. So it means that energy is given out from the system to surrounding. Now in A level, we student has to be able to draw the how you can call it, profile diagram for uh, in this direction. But then in A level also you are to find a way to synthesize or to have this product from the reactant, right? So um, we begin with Na, all right? So we begin with NaS, okay, plus F2G, all right? And then if I use another color, for example, this one, we call this process as a delta HF standard or theta. Yeah. So actually, when you are to find or to evaluate the value of lattice energy, all right, so you have to be able to construct the Born Haber cycle, right? So it means that it is several pathways before we arrive with the product. All right, so finally we can find the value of lattice energy. So in several textbooks, they have a different format of constructions of the Born-Haber cycle, but in my perspective, I feel that this way, the one that I'm going to share to you, is the easiest way to draw the Born-Haber cycle. All right, so again, I have a NaS, right? Reacts to F2 gas, then I have a NaF solid. So we call this reaction is actually delta HF formation, right? So because we form one mole of ionic compound from its element under standard condition. Okay, the standard conditions of Na is solid, F2 is actually gas, and then you have a NaF in the form of solid state. So that's why we are eligible to put theta. All right, and then next is actually I have a Na. Okay, so our intention is basically, right, we have to be able to convert this form into this form. All right, so what is the pathway that we need to take? So NAS to NAG, basically we call this one is delta H atomization. So I just put AT, right? So atomizations, theta means that we form one mole of sodium gas, right? Um, and then in order to convert NAG becomes Na plus G, of course, in AS level, we already learned that we have to remove one electron from the outermost cell. So it is actually delta H theta ionization energy. Ionization energy. So it's actually the first ionization energy. Yeah. So let me just emphasize here, this is actually first because we only remove the first electron from outer cell of sodium atom. All right, so now we have Na plus G. All right, so how about this one? How do we convert F2 becomes F minus? So you only need one F here, but then what we need to do is actually we have to, again, we have to atomize. All right, so F2 becomes F, G. All right, but then if you look at this fraction, so if I may use this space, F2 becomes F, G. So
this one is actually delta H atomizations theta. But then we cannot say that this actually delta H atomizations theta because first and foremost, this equation is not balanced. So you have two F here, but then you have only one F here. But then on the other hand, we need to have a 1 mole of F here, right? So what we need to do, we multiply this one by under half. So now you have to, we already balance this two. So we put here is actually half, right? So once I do this one, it is already balanced. So this one is already balanced, right? So Na1, F is actually 1, half the times 2 is actually 1. So I also have 1 F here. So now I have a delta HF theta of NAF, all right? So now I have a F G. So again, let me label this one is actually delta H atomizations of F. All right, so F2. So you can see how can we progress to the next step. All right, so here, all right, so how to convert this one. Okay, so convert this one, F becomes F minus is actually the value of the first electronic affinity. Electronic affinity. Yeah, so the first value of electronic affinity. It means that we introduce, okay, so Fg plus E minus goes to F minus G. So this is actually first, okay, first electronic affinity or affinity electron of F. Now I have F minus, all right? Okay, so now to to calculate the value of lattice energy, all right, the value of lattice energy. So we can use the equation or simple algebra calculation, all right? So it is obvious that this pathway, so we have atomizations of Na, we add to first ionization energy of Na plus atomizations of F2, and then we add the first electronic affinity or affinity electron of F, and then we add lattice energy is equal to delta HF, all right? So I'll just write here, equation is actually, I just make it short, simple, AT of Na, right? Plus I have a IE, okay? First IE, so let me just erase this one so it make it very clear. All right, so first IE, first IE of Na plus what? Atomizations of F2, all right? Okay, and then plus first, okay, electronic affinity of F, all right? Plus lattice energy equal to delta HF of this one. All right. So now to conclude is how to find lattice energy is actually delta HF. All right. Supposedly all of this value, okay, the one I put in the purple color. All right. So let's say all of this B. All right. So lattice energy is basically delta HF minus B. Now you don't need to worry how do you get this value, because oftentimes you can find either they will tell you the value of atomizations of Na and atomization of F2, or even you have to check, you need to use data booklet to find the value of the first electronic affinity and the ionization energy of sodium is already written there, so you don't need to worry about it. Okay. Okay. The other thing is actually factors, right? So they are mainly factors that affect lattice energy. Okay. So number one is actually charge. Number two is actually radius. All right, so you may use this formula basically. lattice energy is equal to Q1 times Q2 divided by R square. All right, so for simplicity, I'll use this one LE. All right, so for example, if we compare lattice energy between NAF, MgO, and let's say I have a Al2O3, right? So if you are asked to arrange the lattice energy from the most exothermic to the least exothermic, so we can actually use this formula. All right. So first you need to check the charge. So Na is located in group 1, so it will have a +1 charge. F is actually -1, while Mg is actually located in group 2, so it has +2, while oxygen is -2. Al is +3 because it is located in group 3, and oxygen is -2 because it's located in group 6. All right. So if we find the value of Le, we just plug in this value here. So lattice energy for NAF will be 1. Lattice energy for MgO is actually 4 because 2 times 2. And lattice energy for Al2O3 is actually 6. So please disregard the sign. Yeah. So we only need to find the quantity, the number of data only. So it means that basically, yeah, of course, you can also put -6 here, sorry, -4 and actually -1. So when you consider this, right, so the one that most negative will be, will have highest lattice energy. So what's the significance of the highest lattice energy? Highest lattice energy will reflect to the higher of melting point. Okay, so if your lattice energy is very exothermic, it means that very negative. All right, so meaning the melting point of the ionic compound will be very high. If this one is very high, it is because of you'll have a stronger bonding. Stronger bonding between what? Between two oppositely charged particles. In this case, for example, Al 3 plus and O2 minus. So when they have a very strong bonding, then it requires a lot of energy to break them. It corresponds to the high melting point. And then why do we get this stronger bonding? Because the lattice energy of the Al2O3 is very exo, very negative. All right. So if we arrange this one into the strength of bonding, it means that Al2O3 is the strongest um, compared to MgO, and the weakest actually NAF. All right. Okay, so that's the first factor. The second factor that I'm going to highlight is actually the radius. Radius. Okay, so let's say we have a lithium, sodium, potassium, right? And then we pair up with oxygen, oxygen, oxygen. Then you'll have Li2O, you'll have Na2O, then you'll have K2O. We have the same, actually same anion, right? But different cation. All right, so I believe you will agree with me that as we go down the group, the size of either ion or atom increases. All right, so if we plug into the previous formula, Q1, Q2 divided by R square, it means that the radius of K, okay, is actually fact that the radius of K Rk, right? Rk plus is greater than Rna plus is greater than Rli plus. So it means that because R is inversely proportional to lattice energy, it means that I may deduce that lattice energy of Li2O is the most exo compared to Na2O, compared to also compared to K2O. Okay, so K2O is actually the most endo, right? While Li2O is actually the most exo. All right, so you can also check this one, and then you make find it simple. All right. I hope this learning helps you. Thank you so much for watching. Don't forget to like and subscribe. Thank you.